What was there before the universe existed? This is a question that science still cannot answer definitively. We are used to thinking that everything has a beginning. But imagine a moment when there was neither time, nor space, nor even matter. How could the universe we live in arise from this silent void? Modern science offers answers that seem as mysterious as the question itself. Research in particle physics and cosmology suggests that everything we see once emerged from an incredibly dense state. But what was there before that? How could the laws of nature that we study today exist if there was nothing to which they could be applied? If our universe was born from nothing, then what is this nothing? Could the vacuum of space be the source of all that exists? The origin of the universe and the question of how it could emerge from nothing is one of the central mysteries of modern science. The Big Bang theory, which describes the early stages of the existence of our universe, posits that approximately 13.8 billion years ago, the universe was in a state of infinite density and temperature, a singularity. It was from this point that the rapid expansion of space began, a process that continues to this day. However, the Big Bang theory leaves unanswered the question of what existed before this moment, and where the laws of physics governing this process came from. Physicists and cosmologists have long sought to explain how something could arise literally from nothing. Contemporary models suggest that the state of nothing, in a physical sense, may not be absolute emptiness, but rather a vacuum that, according to the laws of quantum mechanics, is not completely devoid of content. In this vacuum, quantum fluctuations can occur, leading to the appearance of particles and antiparticles for extremely brief periods. Such quantum processes might explain how the universe originated, possibly resulting from fluctuations that gave rise to an incredibly dense and hot singularity, which became the starting point for all that exists. However, even accepting the theory of quantum fluctuations and vacuum as a possible explanation for the universe's origin, many unresolved questions remain. Why did this particular universe, with all its physical laws and structures, come into existence? Could there be many other universes, each governed by its unique laws? And finally, what triggered the Big Bang process? Science has yet to provide precise answers to these questions, although research in particle physics and cosmology continues to expand our understanding of the nature of the cosmos. But even if it is possible to explain how the universe could arise from nothing, what about the fundamental particles and forces that underpin its structure? Fundamental particles and forces play a key role in understanding the structure of the universe. To explain what our world is made of at the deepest level, scientists have developed the Standard Model of Particle Physics, a theory that describes the interactions of the smallest particles such as quarks, electrons, and neutrinos, as well as the four fundamental forces: gravity, electromagnetism, weak nuclear force, and strong nuclear force. This model is the result of decades of research and experimentation, and while it explains much of what we know about the universe, it is far from complete. The Standard Model unifies three of the four known forces of nature, the electromagnetic, weak, and strong forces, but it cannot explain gravity, which, despite its weakness at the subatomic level, plays a crucial role on cosmic scales, governing the motion of planets, stars, and galaxies. Gravity, as described by Einstein's general theory of relativity, has yet to find its quantum interpretation, and scientists are working towards creating a unified theory that encompasses all fundamental interactions, including gravity. In addition to gravity, the Standard Model faces other mysteries. One such mystery is dark matter, a hypothetical form of matter that does not interact with electromagnetic radiation, meaning it is invisible to telescopes. It was proposed to explain anomalies in the motion of galaxies and their clusters that cannot be accounted for by ordinary matter. There is also the mystery of dark energy, a force responsible for the accelerated expansion of the universe. Together, dark matter and dark energy account for about 95% of all mass and energy in the universe, yet their nature remains unknown. Despite its achievements, the Standard Model does not answer the question of what constitutes the bulk of the universe's mass. It also does not explain why particles have the masses and properties that we observe. For instance, it was previously thought that neutrinos had no rest mass, similar to photons. Japanese physicist Takaaki Kajita and Canadian physicist Arthur MacDonald were awarded the 2015 Nobel Prize in Physics for the discovery of neutrino oscillations, which shows that neutrinos have mass. This discovery points to the existence of new physics that goes beyond our current theoretical framework, raising questions about how to interpret the limitations of the Standard Model and what it tells us about the nature of dark matter and dark energy. Dark matter and dark energy represent some of the greatest mysteries in modern cosmology. While they constitute the overwhelming majority of mass and energy in the universe, their nature remains unknown. Dark matter was first proposed to explain strange observations regarding the movement of galaxies. According to the laws of gravity, the speeds of stars at the edges of galaxies should decrease as they move away from the center. However, in reality, they remain stable. This led scientists to suggest that there exists an invisible mass within galaxies, which causes such effects. This invisible mass was named dark matter. Dark matter does not interact with electromagnetic radiation. It neither absorbs, reflects, nor emits light, making it invisible to all existing telescopes. Its existence is confirmed only through indirect evidence, primarily its gravitational influence on visible matter and the distribution of galaxies in clusters. Numerous theories have been developed about the nature of dark matter. One of the most popular is the hypothesis of the existence of massive particles that weakly interact with ordinary matter, known as WIMPs, weakly interacting massive particles. The term WIMP was proposed in 1986 by American cosmologist Michael Turner, who is also the author of the term dark matter. However, despite numerous attempts to detect these particles directly using underground detectors and other methods, there is currently no evidence of their existence. The mass of WIMPs is expected to be at least several tens of times greater than that of a proton. Among the possible candidates for WIMPs, the lightest supersymmetric particles, neutralinos, are most frequently considered, as they are stable in most supersymmetry theories. Dark energy is an even more mysterious force responsible for the accelerated expansion of the universe. Its existence was identified in the late 1990s, when astronomers observing distant supernovae discovered that galaxies are moving away from each other at an increasing speed. Today, dark energy accounts for approximately 68% of all energy in the universe. However, its nature remains unresolved. There are three main approaches to explaining the essence of dark energy, each examining its nature and influence on the universe. The first approach treats dark energy as a cosmological constant. This implies that it represents a constant energy density uniformly filling the entire universe. In this context, a non-zero energy and vacuum pressure are postulated, playing a key role in the expansion of the universe. The second approach suggests that dark energy is some form of quintessence, a dynamic field whose energy density can vary both in space and time. This scenario implies more complex interactions than a simple static cosmological constant and suggests that dark energy may evolve under different conditions. The third approach views dark energy as a manifestation of modified gravity at scales comparable to the size of the visible universe. This perspective offers an alternative explanation for the expansion of the universe, linking it to changes in gravitational interactions at large scales. Each of these explanations has its strengths and weaknesses, and remains a subject of active research in astrophysics and cosmology. Both phenomena pose significant challenges for modern science. Dark matter and dark energy not only alter our understanding of the structure and evolution of the universe, but also compel a re-evaluation of fundamental physical laws. These phenomena indicate that the standard model of particles and interactions is incomplete, and that there may exist an entire realm of new physics beyond it that could explain the composition of most of the cosmos. While scientists continue to seek the nature of dark matter and dark energy, how can experimental methods be utilized to delve deeper into these phenomena? Experimental methods play a crucial role in studying the fundamental aspects of the universe. Research in particle physics is closely linked to the creation and use of complex technologies, such as particle accelerators and detectors, which enable scientists to recreate conditions similar to those that existed in the moments after the Big Bang. These technologies help investigate the behavior of elementary particles at extremely high energies, shedding light on many hidden aspects of the nature of matter. One of the key tools for such research is the Large Hadron Collider, LHC, the largest particle accelerator in the world, located on the border of Switzerland and France. The idea for the LHC project originated in 1984 and was officially approved 10 years later. Construction began in 2001 after the previous accelerator was decommissioned. The LHC became famous for the discovery of the Higgs boson in 2012, a particle predicted by the Standard Model that gives mass to other particles. This discovery was a significant step in confirming the theory of elementary particles, but it also indicated that the Standard Model requires modifications. The question of how particles acquire mass remains central to understanding more complex phenomena, such as the nature of dark matter. Scientists are also conducting experiments aimed at the direct detection of dark matter particles. For example, the Xenon research project studies dark matter at the Gran Sasso laboratory in Italy. The Xenon experiment employs a two-phase time projection chamber, TPC, where colliding with atoms in the tank will release photons and electrons, which can be detected as flashes of light. Such signals were first recorded on June 16, 2020, and may provide evidence for the existence of dark matter. These detectors are designed to detect weak signals that may indicate the presence of WIMPs, hypothetical dark matter particles. Despite the lack of direct evidence, each experiment helps refine theories and narrow down search parameters. Another important experimental approach is the study of cosmic microwave background radiation, CMB, which is the residual radiation from the Big Bang. Using satellites like Planck, scientists examine small variations in the temperature of this radiation, allowing conclusions to be drawn about the distribution of matter and energy in the universe, as well as the properties of dark matter and dark energy. However, despite progress in creating detectors and accelerators, no experimental facility has yet provided definitive proof of the existence of dark matter. The question of what other technologies and methods may assist in solving this mystery remains open. Yet how might the results of these experiments influence our understanding of fundamental laws of physics, such as quantum fluctuations and their connection to the emergence of the universe? Quantum fluctuations represent one of the most intriguing and significant aspects of contemporary understanding in physics and cosmology. These fluctuations are temporary changes in energy at a point in space, arising from the Heisenberg uncertainty principle. This principle asserts that certain pairs of physical properties, such as position and momentum, cannot be precisely measured simultaneously. This leads to the conclusion that even in the so-called vacuum, where no matter is assumed to exist, spontaneous appearances and disappearances of virtual particles occur continuously. Quantum fluctuations played a crucial role in the formation of the universe's structure following the Big Bang. During the inflationary period that took place immediately after the Big Bang, slight quantum fluctuations in the density of matter were stretched to the scale of the entire universe. These fluctuations marked the beginning of the formation of large structures, such as galaxies and galaxy clusters. Research indicates that these initial fluctuations later determined the distribution of matter in the cosmos and laid the groundwork for the formation of all the visible structures we observe today. Furthermore, quantum fluctuations can be linked to the formation of particles from the vacuum. In high-energy conditions, such as those near black holes or in the early universe, virtual particles can become frozen and become real. This phenomenon, known as Hawking radiation, describes how black holes can lose mass due to processes associated with quantum fluctuations, leading to the emission of particles. This discovery implies that even under the most extreme conditions, emptiness can become a source of matter. But how do quantum fluctuations relate to our understanding of elementary particles and interactions? And how might this knowledge change our perception of the very nature of matter? Cosmological inflation is one of the most significant theories in physics and cosmology, explaining the early stages of the universe's existence. It posits that for a tiny moment right after the Big Bang, the universe underwent exponential expansion, increasing dramatically in size. The first version of the theory was proposed in the second half of the 1960s by E.A. Glenner, but key contributions to its development were made in the late 1970s and early 1980s. by Alexei Starobinsky, Alan Guth, Andrei Linde, Vyacheslav Mukhanov, and several others. This inflationary period helped resolve several key problems faced by early cosmology, including the horizon problem and the flatness problem. The horizon problem arises from the observation that distant regions of the universe have nearly the same temperature, despite the fact that they could never have interacted with each other since light from one region would not have had time to reach the other due to the finite speed of light. Inflation offers a solution to this problem by asserting that all these areas were once close to each other under conditions of high density before being pushed apart due to inflation. Thus, before the onset of this rapid expansion, they had the opportunity to reach thermodynamic equilibrium, resulting in the temperature uniformity we observe today. The flatness problem concerns why the universe appears so close to geometrical flatness on large scales. In the absence of inflationary expansion, the universe could either be highly curved or expand, but inflation, by smoothing out any initial curvature, has led to the universe currently appearing flat, as confirmed by observations of the cosmic microwave background radiation, CMBR. These observations indicate that the temperature fluctuations in the CMBR match the predictions of the inflationary model, confirming that this period existed and influenced the structure of the universe. Inflation also provides an explanation for the origin of large structures in the universe. It suggests that tiny quantum fluctuations, stretched during inflation, became the seeds for the formation of galaxies and other astronomical objects, as gravity began to pull matter into these regions, creating conditions conducive to the formation of stars and planets. However, despite its successes in addressing several issues, inflation also raises many questions. How might these questions about the nature of inflation be connected to a deeper understanding of the laws of physics that govern the behavior of matter and energy in our universe? Formation of atoms is a key stage in the history of the universe that occurred approximately 380,000 years after the Big Bang, when it began to cool and expand. At this time, although protons and neutrons already existed, the temperature of the universe was too high for electrons to combine with them to form neutral atoms. The universe at this point was a cloud of ionized gas, where free electrons interacted with photons, preventing light from passing freely. As the temperature dropped to about 3,000 degrees Kelvin, conditions became suitable for recombination, the process in which electrons began to bind with nuclei, forming neutral atoms. This process altered the interaction between light and matter, allowing photons to move freely throughout the universe. As a result, the release of cosmic microwave background radiation, CMB, occurred, which we observe today as a faint radiation uniformly distributed across the sky. This first light became important evidence for the Big Bang theory and opens a window into the early stages of the universe's history. There is also a theory of the plasma universe, which is a relatively new hypothesis in cosmology that suggests the universe is primarily composed of plasma, a highly ionized state of matter, and that the interactions between plasma and electromagnetic fields are the key driving forces determining the behavior of celestial objects. The plasma universe theory was first proposed in the 1970s by physicist and astronomer Hannes Alfvén. The process of atom formation not only marked a turning point in the evolution of the universe, but also laid the groundwork for the subsequent formation of stars and galaxies. The neutral atoms formed during recombination began to condense under the influence of gravity, creating primordial gas clouds. These clouds served as the material for the formation of the first stars, which in turn became the primary factories for producing heavier elements through nucleosynthesis processes. Stars synthesized elements such as carbon and oxygen, which are essential for forming planets and ultimately life. How exactly these primordial atoms organized into stars and galaxies, and how these initial processes of atom formation relate to subsequent stages of matter evolution, such as nucleosynthesis in stars, remains a significant area of inquiry. Nucleosynthesis is a key process that occurred after the formation of the first atoms and became the foundation for the creation of more complex elements in the universe. It involves nuclear fusion reactions taking place in stars and was one of the most important stages in the evolution of matter following the Big Bang. Immediately after recombination, when the first neutral atoms formed, the universe was predominantly composed of hydrogen and helium. However, to create all the elements necessary for the formation of stars, planets, and ultimately life, it was essential to synthesize heavier elements. The process of nucleosynthesis in stars begins when hydrogen atoms, protons, start to combine into more complex structures under the influence of immense temperatures and pressures in their cores. Under these conditions, hydrogen can fuse, forming helium through a series of thermonuclear reactions known as hydrogen burning. This is the primary process that occurs throughout much of a star's life. A tremendous amount of energy is released in this process, which keeps the star stable, counteracting gravitational collapse. As the hydrogen supply in a star's core is depleted and the star ages, the pressure and temperature at the center of the star increase, allowing helium to start fusing into heavier elements such as carbon and oxygen. This process is called helium burning and occurs in the later stages of stellar evolution. In stars that are significantly more massive than the Sun, even more complex nucleosynthesis processes can occur, including the synthesis of elements up to iron through successive stages known as carbon, neon, and silicon burning. What other nucleosynthesis processes occur in stars, and how do they influence the chemical composition of future stellar systems and planets? Elements formed in stars become the building blocks for the formation of new stellar systems and planets, creating a complex network of interactions in space. When stars die and expel their elements into interstellar space, they enrich the surrounding gas and dust, which can later condense and form new stars and planets. This process begins with the formation of molecular clouds, cold and dense regions where gravity begins to dominate over internal pressure, allowing gas and dust to compress and form compact structures. In the early stages of formation, stellar precursors known as protostars begin to accumulate material from their surroundings. As their mass and temperature increase, nuclear fusion starts in their cores. This process leads to the birth of a new star, which begins to glow and emit energy, generating heat and light that permeate the surrounding space. This radiation also influences the clouds of gas and dust with which the star interacts, causing them to compress and potentially initiating the planet formation process. As a result of such interactions, protoplanetary disks can form, flat structures of gas and dust surrounding a young star. Within these disks, through processes of accretion and collision, planetesimals, small bodies, form and can merge to create larger planets. The theory of planet formation, which includes the so-called planetesimal hypothesis, was proposed in the late 19th and early 20th centuries by American scientists Molteno and T. Chamberlain. In the USSR, this hypothesis was further developed by astronomer V. Safronov, and it is currently supported by the majority of astronomers worldwide. The process of planet formation in protoplanetary disks is a key element in the development of stellar systems, vividly demonstrating how elements created in stars can become the foundation for forming new worlds. Furthermore, interactions between stars in dense regions of galaxies can lead to the capture and recycling of matter, contributing to the diversity of planetary systems. For example, stars may collide or pass close to one another, causing gravitational interactions that alter their orbits and redistribute matter. This can result in planets formed around one star being ejected into interstellar space, or, conversely, captured by another star. The formation of planets and stellar systems illustrates how elements created in stars become the basis for new creations. However, the question remains of how exactly the conditions on these planets influence the emergence and development of life, and what factors might determine whether a planet becomes habitable or, conversely, lifeless. The formation and development of life on planets depend on numerous factors, including chemical composition, atmospheric conditions, the presence of water, and the stability of climate changes. These factors are largely determined by both internal processes on the planet itself and external influences, such as radiation from the star it orbits. On planets with temperatures that are too low or too high, life is unlikely to be possible. An optimal temperature that allows for the existence of liquid water is considered a necessary condition for the emergence and evolution of living organisms. Interestingly, the study of exoplanets, planets located beyond our solar system, offers new perspectives for the search for life. Astronomers are actively investigating stars and their planetary systems in an attempt to detect signs of potentially habitable worlds. Subscribe to the channel and stay tuned for news so you don't miss discoveries that could change your understanding of the cosmos.